Okay, so quantum computing, huh? It's like the buzzword of the decade.
Yeah, everyone's talking about it, right?
But is it really all that? Or is it mostly hype?
Well, I think it's safe to say something big is happening. Like, we've been writing Moore's Law for, what, decades now? Smaller, faster, more powerful computers.
Like,
But we're hitting a wall,
literally a wall. Like, we can't physically shrink things any smaller.
pretty much. We're talking atoms here. And at that level, the old rules, they kind of go out the window.
This is where Michio Kaku comes in, right? With quantum supremacy.
Exactly. He breaks it all down, this whole new frontier.
So help me out here. What exactly changes at the atomic level? Why is it so different?
It's where quantum effects take over. Things get weird, even for physicists.
Weird how? Give me an example.
Okay, so imagine a single electron. Now, in the quantum world, that electron can be in multiple states at the same time. It's called superposition.
Superposition. Okay, that's already messing with my head.
It's a trip, right? It's like that whole Schrodinger's cat thing.
Oh, the cat that's both alive and dead.
Exactly. Until you open the box, it exists in this weird both-and state. It's like that with electrons and quantum stuff. They're not just one thing or the other until you measure them.
So if we're talking computers, how do you go from cats in boxes to, like, ones and zeros?
Good question. Instead of bits, quantum computers use qubits.
Okay, so what's the difference?
A bit is like a light switch, on or off, 0 or 1. But a qubit, because of superposition, can be both 0 and 1 at the same time.
Hold on. Let me see if I got this straight. It's like a coin spinning in the air. It's both heads and tails until it lands.
You're getting warmer, but it's even weirder than that. It's not just that we don't know if it's heads or tails, it's that it's actually both at the same time. Mind-blowing, right?
So instead of just two options, on or off, you've got, like, infinite possibilities.
Exactly, and that's where the real power comes in.
Okay, I'm with you so far, I think.
Yeah.
But how does that actually make a computer faster or better? What's the practical difference?
Think of it this way. Imagine searching for a single answer in a giant library.
Okay, I'm picturing it. Huge library, millions of books.
On a normal computer, it's got to go one book at a time. But a quantum computer, it can be in multiple places at once, checking every book simultaneously.
Whoa, so it's like having, like, a million helpers all searching at once.
Right. Exactly. That's the basic idea. It's a completely different way of approaching problems, made possible by this quantum weirdness.
Okay, this is already blowing my mind, but then there's entanglement, right?
Yes, entanglement. Einstein called it spooky action at a distance.
And is it as spooky as it sounds?
It's more like deeply strange, but also really cool. Imagine two of those spinning coins again. Entanglement means if one lands on heads, the other instantly flips to heads no matter how far apart they are.
So, like, you're linked, even across the universe.
Precisely. It's like an invisible thread connecting them. That's entanglement.
And this is important for quantum computers.
Absolutely. Entanglement is what allows these qubits to interact in ways that regular bits can't, making these massively parallel computations possible.
So superposition and entanglement, those are the two big superpowers we're talking about.
You got it. And with those two things, quantum computers have the potential to solve problems that would take classical computers, even the most powerful ones we have today, billions of years.
Okay, that's impressive and kind of scary. But give me an example. What kind of problems are we talking about? What can a quantum computer actually do?
Think about things like revolutionizing medicine, designing brand new materials, or even figuring out how to make fusion energy a reality.
Wow, okay. We're talking about changing the world here.
That's exactly what Kaku argues. It's about opening up possibilities we can barely imagine right now.
Okay, so let's start with something a little less abstract, like medicine. How could quantum computers actually change healthcare?
Imagine being able to design drugs at the molecular level, like seeing how each atom interacts with the body.
So instead of years of lab work, we could test things out on a computer first.
Exactly. We could target diseases more effectively, personalize treatments, maybe even cure diseases that are considered incurable today. It's huge.
That's incredible. But what about the risks? I mean, I've heard people say that quantum computers could be dangerous too, right?
Right. There are definitely concerns. One big one is security.
What do you mean? Like hacking?
Even more than that, the encryption we use for everything online, our bank accounts, our personal data, quantum computers could potentially break through all of that.
Seriously. So everything becomes vulnerable.
That's the worry if we're not careful. Kaku talks about how there's this whole race going on to develop new types of encryption, ones that even quantum computers can't crack.
So it's like a cat and mouse game, constantly trying to stay ahead of the technology.
Exactly. And it's high stakes, right?
Yeah.
Because this technology is so powerful.
Okay, that's a little unsettling. But speaking of powerful technology, we can't forget about AI, right? How does this all play into the future of artificial intelligence?
That's a big one, and it's something Kaku explores in detail.
So lay it on me. What's the quantum AI connection?
Imagine AI systems that can actually design new materials from scratch or optimize complex systems like traffic flow in a city, even understand and translate languages perfectly.
Okay, now that's both exciting and a little terrifying. How would quantum computers even make AI that much smarter?
It comes down to processing power. Quantum computers could crunch through data in ways we can barely comprehend right now, finding patterns, making connections that would take classical computers centuries, maybe even millennia.
So it's like giving AI a brain boost, but on a whole other level.
You could say that. But remember, we're still in the very early stages of all of this. It's like we just discovered fire, and now we're trying to figure out how to build a civilization with it.
Okay, I'm with you on that. It's incredible, but also a little overwhelming. So how does it actually work in practice? What are the building blocks of a quantum computer? I mean, it's not like they're using tiny cats in boxes,
Not
right?
quite. It all comes down to these qubits we talked about. But building them and controlling them, that's the hard part.
What do you mean? What's so hard about it?
It's like trying to build a watch, but instead of gears, you're using individual atoms. It requires insane precision. And keeping those qubits stable, that's a whole other challenge.
So what's the secret sauce? How do they actually do it?
There are a few different approaches, but one of the most promising is using superconducting circuits. Superconducting. Like zero resistance. Isn't that how those maglev trains work?
Exactly. At extremely low temperatures, some materials can conduct electricity with zero energy loss. It's another one of those quantum phenomena.
So they build these tiny circuits, cool them down to almost absolute zero, and then magic happens.
Pretty much. It's like creating a tiny, perfect electrical circuit that operates by the laws of quantum mechanics.
Okay, so incredibly difficult, but also incredibly cool. But you've lost me a little bit on this whole qubit thing. I'm still trying to wrap my head around how something can be in two states at once. It just seems impossible.
I hear you. It definitely goes against our everyday intuition. But the math checks out. The experiments back it up. The quantum world, it plays by a different set of rules.
Okay, so I just gotta trust the physicists on this one, huh? Pretty much. And the more we learn about quantum mechanics, the more we realize we don't know. It's a humbling and exciting field.
Well, it's definitely humbling for me. I think we've covered a lot of ground in this first part of our deep dive.
Yeah.
The basics of quantum computing, the potential benefits, the challenges,
We've just scratched the surface.
but there's still so much more to unpack, right?
Oh, absolutely. In the next part of our deep dive, we'll dive even deeper into the specific ways quantum computers could change the world, from medicine to material science, energy production, artificial intelligence. It's going to be a wild ride.
I'm ready. This quantum stuff is definitely mind-blowing. Okay, so last time we talked about quantum computers, right? And how they could like totally change everything, from designing new drugs to how AI works.
It's a lot to wrap your head around.
Totally. But one thing that really struck me reading Kaku is how he ties all of this back to the history of science.
It's all connected, isn't it? He talks about how our understanding of chemistry went through this massive shift when quantum mechanics came along.
Right, like how electrons behave and how that determines how elements interact and all that.
Exactly. It all boils down to Schrodinger's equation. This, like, elegant piece of math that basically revealed chemistry is, at its core, quantum mechanics in action.
So like all those chemical reactions, the stuff that makes life possible, it's all driven by these tiny quantum particles doing their thing.
It's all about how these tiny particles interact and behave. It's like zooming in on a tapestry, right? You see this complex picture, but it's all just threads woven together in a specific way.
Okay, I get how that ties into like designing new materials, but what about something like, I don't know, energy production? How does quantum computing fit into that picture?
Well, let's take solar energy, for example. Kaku talks about how plants, through photosynthesis, they've mastered capturing energy from the sun way more efficiently than we can.
Right, and we've been trying to replicate that with solar panels for like forever.
Exactly. And that's where quantum computers come in. They could help us, like, really unravel the secrets of photosynthesis, how it works at the molecular level, so we can design way more efficient solar cells.
So we're not just copying nature, we're using quantum computers to potentially design even better solar cells than nature itself.
Precisely. And it's not just about making them more efficient either. It's about finding new ways to store that energy, distribute it. We're talking about a whole new energy grid.
Okay, now that's a game changer. But what about fusion power? I feel like that's the holy grail, right? Clean, limitless energy, but always just out of reach.
And yet, Kaku seems optimistic, He says fusion power is a question of when, not if, and that quantum computing could be the key to unlocking it.
Really? That's a bold statement. What makes him so confident?
Well, fusion requires insane levels of precision and control, right? You're dealing with superheated plasma, and that's where quantum computers come in. They can help us model and manage these incredibly complex magnetic fields.
So it's like instead of trying to contain an explosion, we're trying to orchestrate it.
That's a great way to put it. And just like a conductor shapes the sound of an orchestra, quantum computers could help us, fine-tune and control these fusion reactions.
Okay, now we're talking about some seriously powerful stuff. But, with great power comes, well, you know the rest. Are there downsides to this technology?
Of course, any powerful technology can be used for good or bad, right? And Kaku does address some of those concerns, one of the big ones being job displacement. As these quantum computers get more sophisticated, they could automate tasks currently done by humans.
Yeah, that's a big one. Automation is already a hot topic, and this could accelerate things even more.
It's a real concern, but Kaku also emphasizes the importance of education and retraining. He believes we can prepare people for this quantum future. It's not just about the technology, but about how we adapt to it.
Makes sense.
Yeah.
So it's not all doom and gloom. It's about embracing the change, but also making sure everyone benefits from it.
Exactly. It's about building a future where this technology works for all of us.
Well said. Now, you mentioned earlier that quantum computers could analyze huge amounts of data, right? Like way more than we can imagine. How would that work in, say, the real world?
Imagine you have a haystack, right?
Yeah.
And you're looking for one specific needle. That's what data analysis is like for classical computers. But a quantum computer, it can be in multiple places at once. It's like searching the entire haystack simultaneously.
Okay, so it's like having a superpowered search engine that can instantly find exactly what you're looking for, even in a mountain of information.
Exactly. And that has huge implications for fields like medicine, finance, even astronomy. We're talking about finding patterns and making connections that we could never see before.
Okay, break it down for me. Let's start with medicine. How could this level of data analysis change things?
Take personalized medicine, for example. With quantum computers, doctors could analyze a patient's entire genetic makeup, lifestyle, environment, everything.
So we're talking about treatments that are tailored to each individual person.
Precisely. No more one-size-fits-all approach. It's about understanding the specific needs of each patient and developing treatments accordingly.
Wow, that's incredible. What about finance? It seems like another field that's drowning in data.
Absolutely. Quantum computers could analyze market trends, assess risk, and make investment decisions with a speed and accuracy that's impossible for us right now.
So potentially we could make smarter investments, prevent financial crises.
It's definitely within the realm of possibility, but, with any powerful tool, there's always the potential for misuse.
Right, we have to be careful, make sure it's used ethically.
Precisely. It's a conversation we need to have. But let's not forget the positive potential here. We could use this technology to solve some of the world's biggest problems: climate change, poverty, disease.
It's a good reminder that technology is a tool, and it's up to us to use it wisely. Now, you mentioned astronomy earlier, and I'm curious, how could quantum computing help us explore the cosmos?
Well, for one, it could help us analyze the insane amounts of data that telescopes collect, right? Imagine seeing further and clearer into the universe than ever before.
So we're talking about discovering new galaxies, maybe even finding evidence of life out there.
Those are definitely exciting possibilities. But it's not just about what we can see, right? It's about understanding what it all means. Quantum computers could help us unlock the secrets of dark matter, dark energy, maybe even figure out how the universe began.
Wow. Okay, so we're not just talking about a new era of discovery, but a whole new understanding of our place in the universe.
Exactly. It's a fundamental shift in how we see ourselves and the cosmos. But before we get too carried away, maybe we should bring things back down to Earth for a bit.
Right, because as amazing as all this sounds, it's still pretty abstract. So how do we actually build and access these quantum computers? Is this something that only governments and tech giants will have?
That's a key question, and thankfully things are changing rapidly. Right now, yeah, it's mostly big institutions with the resources to build and maintain these machines. They're complex and expensive, but we're seeing more collaboration between universities, companies, even governments.
So it's like the early days of the internet, where everyone realized this was a big deal and they needed to work together.
Exactly. And just like the internet, we're seeing cloud-based quantum computing platforms emerge, where researchers and businesses can access this technology remotely.
So you don't need to build your own quantum computer. You just log in and, like, borrow someone else's.
That's the idea. And that's a game changer because it opens up access for smaller companies, universities, even individuals.
That's really encouraging to hear. It feels like quantum computing is moving from, like, science fiction to something more tangible. But let's be real, there are still hurdles.
Oh, absolutely. We're still in the early stages, and building large-scale, reliable quantum computers is a massive engineering challenge.
What are some of the biggest obstacles that they're facing?
Scalability is a big one. Right now, we're working with a relatively small number of qubits.
And more qubits means a more powerful computer.
Exactly. But as you add more qubits, they become harder to control, more prone to errors.
So it's like trying to build a house of cards, but the wind keeps picking up.
That's a pretty good analogy. It's a delicate balancing act.
So how do we overcome that?
Well, there are a lot of brilliant minds working on that, and Kaku highlights some promising approaches. One is something called topological quantum computing, which uses these exotic particles called anyons.
Ennians. That sounds made up.
I know, right? But the quantum world is full of surprises. The point is, there's a lot of research and development happening, and the pace of innovation is incredible. So while we're not all walking around with quantum computers in our pockets yet, the future of this technology is definitely something to be excited about.
I like the sound of that.
Ah.
But before we get too carried away with the future, what about the near term? What are some of the more immediate applications of quantum computing that we might see in the next few years?
One area where we're already seeing progress is material science. Remember how we talked about how quantum mechanics changed how we understand chemistry?
Yeah.
Well, quantum computers take that a step further, allowing us to simulate the behavior of materials at the atomic level.
So instead of mixing things in a lab and seeing what happens, we can test things out virtually.
Exactly. We could design lighter and stronger materials, more efficient solar cells, even new drugs that target specific diseases more effectively.
So it's like having a virtual laboratory where you can play around with the building blocks of matter.
That's a great way to put it. It's about going from discovery by chance to design by intention.
That's amazing. It sounds like we're talking about a whole new era of technological innovation. Are there other fields where we might see similar breakthroughs in the near term?
Optimization problems are another area where quantum computers are already showing a lot of promise.
Okay, what exactly is an optimization problem?
Think about things like logistics and supply chain management. Imagine trying to figure out the absolute best delivery routes for a fleet of trucks, taking into account traffic patterns, fuel efficiency, delivery deadlines, all of that.
Sounds complicated.
It is. As the number of variables grows, it becomes increasingly difficult for classical computers to find the absolute best solution. But quantum computers, they can explore all those possibilities simultaneously.
But faster deliveries, less fuel consumption, maybe even fewer traffic jams.
Exactly. And it's not just about logistics. Quantum computing can be applied to optimization problems in finance, healthcare, artificial intelligence, pretty much any field you can think of.
It's pretty mind-blowing stuff. But before we go any further, I think it's important to come back to reality for a second. We've covered a lot of ground, talk about some incredible possibilities, but we're still in the very early stages of all of this.
It's true. We have to be careful not to get too carried away.
So for our listeners who are probably just as amazed and confused as I am right now, what's the key takeaway here? What should they be paying attention to as this field continues to develop?
I think the most important thing is to stay curious, stay informed. This is a rapidly evolving field, and new breakthroughs are happening all the time.
So read everything you can, talk to experts, don't be afraid to ask questions.
Exactly. The more we understand about this technology, the better equipped we'll be to navigate the opportunities and challenges that lie ahead.
Well said. This has been an amazing conversation. We've talked about the science behind quantum computers, their potential to revolutionize countless industries, and even some of the philosophical implications.
It's been a pleasure exploring these ideas with you.
But there's still so much more to discuss. And next time, we're going even deeper, diving into some of the philosophical questions raised by this technology.
It's going to be a fascinating conversation.
Oh, I can't wait. This quantum stuff, it really makes you think. To our listeners, if you're feeling even a fraction of the awe and maybe slight terror that we are right now, stick around. Okay, so we've talked about how quantum computers work, their potential to revolutionize, well, everything. But let's get a little, I don't know, philosophical for a bit. Kaku doesn't shy away from the big questions, does he?
Not at all. That's what makes quantum supremacy so fascinating. He takes these mind-boggling scientific concepts and connects them back to how we understand reality itself.
It's are we living in a simulation? Is that what we're getting at?
He actually touches on that, believe it or not. But even just the fact that we can ask that question now, it shows how quantum thinking is changing things. If these machines can theoretically simulate reality at the most fundamental level,
then how do we know our reality isn't also some kind of giant quantum computer?
Precisely. It's a mind-bending thought experiment, and while we're nowhere near proving or disproving it, it just shows how quantum mechanics forces us to rethink, well, everything.
Okay, yeah, I might need another coffee for this. But let's maybe bring it back down to earth for a minute. Even without going full simulation theory, quantum computing could still change how we approach some pretty big questions, right?
Absolutely. One example Kaku talks about is the search for extraterrestrial life.
Wait, really? How's that even related? We're going to have quantum-powered alien detectors now.
Not quite detectors, but think about it. Searching for signs of life out there means analyzing these incredibly faint signals, sifting through mountains of data from radio telescopes.
And that's assuming, of course, that aliens are even trying to contact us using technology we understand.
Exactly. But a quantum computer, it wouldn't be limited in the same way. It could analyze those signals differently, search for patterns we haven't even thought of, maybe even decipher forms of communication that are completely alien to us.
So it's not just about having a more powerful telescope, it's about having a whole new way of understanding what we're even looking at.
Exactly. It's imagine trying to decipher hieroglyphics by hand, right?
Yeah.
Now imagine having a machine that can instantly translate entire ancient libraries. That's the kind of leap we're talking about.
That's incredible. And to think we're still just scratching the surface of what this technology might be able to do. What will future generations be capable of?
It's mind-blowing, isn't it? And that sense of wonder, that's what Kaku really emphasizes. He reminds us that every scientific revolution, from the telescope to DNA, it changed our understanding of ourselves and the universe.
And quantum computing feels like that next big leap.
It really does. It's not just about faster computers or new gadgets. It's about a fundamental shift in how we see and interact with reality itself.
Well said. This whole deep dive has been, honestly, a wild ride. From the nitty-gritty of how these things work to these big philosophical questions.
It's been a pleasure exploring these ideas with you.
Likewise. And I think Kaku says it best. This isn't something to be afraid of, but something to embrace. The quantum world, it's full of possibilities waiting for us to explore them.
Absolutely. If we're brave enough to ask the big questions.
Could have put it better myself. So, to our listeners, if you're feeling even a fraction of the awe, the inspiration, maybe a little bit of existential dread, we get it. But go out there, learn more. Pick up quantum supremacy, dive into the research, and who knows, maybe you will be the one making the next quantum leap.
I have no doubt there are many more breakthroughs on the horizon. This is just the beginning.
And we'll be here to dive into them with you. Thanks for joining us on The Deep Dive. Until next time, stay curious.